My name is Kiran Vispute. You can call me Kiran. Today I'll be giving you a presentation about my IBM Data Science course project. It was a capstone project and the topic I chose was credit default in banking system, especially with respect to credit cards. Over the next 15 minutes, I'll be taking you through my project, so stay tuned. So initially we'll be discussing what are the contents of the project. I'll be taking you through the workflow of this entire presentation. The presentation starts with domain background of the banking industry, followed by the problem statement that we are about to solve today. This further goes ahead with the dataset, that is the use case dataset on which we'll be applying the machine learning algorithms, the dataset of the exploration, the data cleaning and feature engineering that we'll be applying on this data, the model definitions and the training, model evaluation metrics and performance, and finally the model deployment. So just to give you a domain background about the banking industry, in banking industry, a customer with a potential credit default is very risky for business. This not only impacts the bank's bottom line, that is in terms of profitability, but also the regulatory guidelines that it has with the Reserve Bank or the central bank in terms of its NPA. So extending this kind of credit is risky for customers as well as banking, and it is not very good decision for banks' financial health. While risk management is an important field in banking when we are talking about credit cards. So a credit risk will be the first line of defense for any credit decision, and performing credit risk management allows banks to minimize the risk associated with credit cards, such as avoiding in case of credit limits for risky customers. Moving ahead, we have the problem statement. So in any organization, if we notice the credit default is not a single stop solution or a single stop problem. It usually gradually develops over a period of time, and there are several indicators which can be used to anticipate the final outcome, such as late payments and the calls to the customers about the different products. By using such patterns, it is possible to prevent the credit default or at least have an idea about the potential credit defaults the customer will be able to make in case he does not make the payments for a continuous extended duration of time. So the goal of this project is to predict the credit card defaults with the help of statistics, machine learning and deep learning algorithms, and with the help of these algorithms we should be able to predict in the 4th or 5th month itself that the customer is going to default in the 6th month. Moving ahead, the dataset that we'll be using for this project is an open source dataset from Kaggle. The Kaggle, it contains 30,000 user records with 26 features that includes demographics and payment status history. If you'll be able to see in the snapshot of the dataset that I have attached, it contains the credit limit balances, the education, the marital status, the age, the payment history in the payment spread out into the months, the bill amount that was generated that the customer was supposed to pay, and the payment amount, the actual payment amount that the customer has made. Moving ahead, like we see the use case. So like I said earlier, the goal is to train a model with the capability to minimize the risk predictions based on the data sets. So using this model, the model predicts whether the late paying customer will be able to pay for an extended duration of time. Like for example, he'll be able to pay his credit default in the 4th or 5th month, or will he be defaulting it further and making it as a credit default. Just to give you an idea, in case the customer does not pay, a credit default is a process in case where the customer does not pay for an extended duration. So for example, if the customer does not pay for the period of 6 months, the credit default is treated as defaulted customer. However, if he pays within those framelines, the customer can escape with a minor penalty. So the evaluation matrix that we'll be using for this model is 4 matrix, the recall and the precision forming a major part of that. So those two are calculated by looking at the below 4 possibilities. One is the true positive case, the false positive case, the true negative, and the false positive. So a true positive is where the model has also predicted the customer will default and the customer has actually defaulted the case. A false positive is a case where the model predicted them as defaulted. However, the customer did not default and he paid his credit card dues or outstanding to the bank. A true negative is a case where the model did not predict them or model failed to predict them as defaulted. However, the accounts did not default and the customer had paid his outstanding. And a false negative, which is the most dangerous situation of all the above three possibilities, is where the model also failed to recognize the customers who will be defaulting and the customers finally defaulted the case. So the use case further we'll be moving ahead with is the project design, the data pre-processing. So we'll be checking for outliers and removing 10 to 25% of the leading and trailing data which have narrow outliers, or if there are any other outliers present, we'll be eliminating those as well. So, and in case of visualization, we'll be visualizing the data to check the correlation and try to find a pattern first visually, and after we'll determine if supervised learning algorithm will be employed. Training and testing. So we'll be splitting the data set into training and testing sets differently. So 70% of the data set will be used as a training, as a learning for machine learning algorithm, and the remaining 30% will be used as a testing set to ensure that the model is robust and we are getting the desired outcomes. Now we move ahead with the data preparation. So initially we have imported the data, as you can see, from a local file itself. We have imported the data as a CSV file. We have checked the headers and the data seems to be imported correctly. Moving ahead, we have to prepare the data for actual regression testing and the model evaluation. So what we do is, first we check if the data contains any null sum. So none of the values in the data have to be null since they influence the data evaluation characteristics. We rename the column pay 0 to pay 1 since pay 0 could not be a 0 month. It has to be the first month that the customer must have made the payment. Second parameter is transforming the lowercase names from uppercase, just for visual simplicity. Third, we'll be eliminating the index column as a part of feature reduction. Moving ahead, the attributes that we can see in the data are 30,000 records across 23 variables as explanatory variables that are extracted from. So like I said earlier, the data includes the limit balance, sex, education, marriage, age, and the payment history of the customer. To know the categories present in the categorical features, we have spread the data into its respective categories and the unique data that is present in each of the categories. So as you can see, there are 2 categories for sex, there are 7 categories for education, 4 categories for marriage, and so on. So moving ahead, as a part of data cleansing, we'll be cleaning the data to arrive at the most optimum values and eliminating the redundant parts. So in case of education, for example, 1 means a graduate school, 2 means a university, 3 means a high school, and 4 means others for which the data is not known to us. And 0, 5, 6 are the values for also which we do not have a known value for the data. So what we do is we categorize it in the others column. So values, so data, education column having values 0, 5 and 6 are recategorized to 4, which means others. By this way, we minimize the data categories and the outliers in the data. Moving on to the data exploration and descriptive analytics. So we describe the data and we see that across the count we have a data limit of 30,000 entries in the data with a mean variance of 167,484, that is 167k. The average credit card limit is 167k and the maximum limit is 1 million. So that drives the standard deviation to 129,748. The average age of credit card holder is also 35 years of age. Moving ahead, what we analyze in the data visualization and data exploration is the past payment delays. The past payment delays, we can notice that there have been some payment defaults. However, they have also recovered in the past 2 to 3 months. So some of them have a clean payment history and some of them have defaulted. If we plot the distribution delays for past 6 months, we notice that some of the customers have already paid 2 months in advance. When the credit card payment was due, they have paid 2 months in advance. And most of the customers have paid the credit card bills on time. So here you can see if the payment distribution is spread over the horizon of 6 months, we can see most of the customers have paid right on time. However, our concern and the area of analysis is the timeline from 0 months to negative onwards, where payments have been lagging. The customers were not able to pay the credit card bills on time, and this can be an indicator of the financial health crisis on part of the customer. We have also analyzed what is the outstanding credit and the respective bill amounts similar to the payment history that we have analyzed further, and the payments that the customer has done in previous months. We have also analyzed that in terms of counts and means. So here also we have a feature exploration of the data, and one more graph plot where we have analyzed is the credit limit across the customer database. So here if we can see, most of the customers that have been issued credit cards fall in the lower middle class and the middle class part of the data. There are very few credit cards issued to HNI customers, that is the high net worth individual. So this decreasing graph over the higher credit balances signifies that most of the credit card holders are in the lower brackets of earning and the. So after importing the data and the initial data exploratory analysis, we come to the most important part of the project, which is exploring the credit default. If you see the plot below, a bar graph which tells us that almost 22% of the 30,000 observations have defaulted the credit card payments. If we go into further data visualization, we'll notice the following bar plots in absolute terms. So the bar plots are spread across the attributes of sex, marriage, age categories, and education. Looking at the bar plots, it will be fair enough to say that the higher default rates are among the higher age group of males who are single and with a lower education background, and an age category which is above 50 years of age. So a further insight into data visualization can be provided with the help of a Seaborn plot, that is a correlation matrix. If we see here, the correlation and the default payment is positively correlated with education, age, and negatively correlated with the limit balances and the payment terms that the customer has made. So moving ahead, we have the feature engineering terms and the ETL. So for feature engineering, like I said earlier, we have split the data into training set and testing set. The training set accounting for 70% of the data, and the remaining 30% is used for testing the model. If you see the train and test shape, that is 21,000 rows are allocated for training, and the remaining 9,000 rows of the data is allocated for testing set. The feature selection. In terms of feature selection, we have used the select k-best method for feature selection to identify the exact features that will help us and get the correct model predictions. Okay, so in terms of feature scaling, we have used the ANOVA selector as a feature scaling and use it as a pre-process to transform our X being the training set and the preparation set. Moving ahead, we have the visualization function to plot the ROC curve and also finding the area under the curve parameters. We have coded that as well in our feature engineering itself. Processing on to the model definition and training, we'll move ahead to the slide. So model selection and definition. The following algorithms we have used for the model selection and definition, as this is a classification problem where using the data, we identify if the credit customer has defaulted or not. So there are only two outcomes based on which the prediction algorithm is supposed to make a prediction whether the customer will default or the customer will not default. So the algorithms that we have used for logistic regression, random forest, boosted trees, deep learning using Keras and TensorFlow, the decision trees, and a naive Bayes classifier. Like I said earlier, the training data is split into a training set and a test data set, accounting for 70% and 30% of the global database. So if we see here, the model evaluation matrix. So like I said earlier, since it is a classification problem, the performance measures of the models will be different. We'll first have the accuracy, which is the total number of predictions that are correct. The precision, that is the total number of positive predictions that are actually correct out of the total universe. A recall function where the proportion of positive observed values are correctly predicted. And the ROC curve and the AUC, that is area under curve. So which metric should we be using? Like we discussed earlier, we'll be using a false positive, false negative, and false negatives are the worst. We'll be looking at recall function. So if we go ahead with what are the model performance indicators and the machine learning algorithm outcomes that for the models that we have used, we see a logistic regression that gives us a training accuracy of 78% and an area under curve of 65%. Similarly, the random forest classification algorithm gives us a perfect training accuracy and a correct prediction of 100%. However, the model perfectly predicts the outcomes from the testing dataset provided. The ROC and the area under curve is 1 because of the minimum of the positive class is higher than the maximum of the negative class in terms of random forest classification. It may also be a case where the model is overfitting and we should be looking at overfitting data. Third, we have feed-forward deep neural nets wherein the model gives us a test accuracy of 78% and an area under curve of 50%. Coming to the other methods of evaluation, we have model performance indicators across other algorithms as logistic regression, naive Bayes, and null set, wherein we get an accuracy of 77% in logic regression, 37% in naive Bayes, and while testing for a null set, we get an accuracy of 77.9%. The last part of the presentation is the actual model deployment, where we actually review the performance of model in comparison with the other individual predictions. So we have given a sample prediction to the model and we'll test if the model is able to perfectly predict if the customer, given the data inputs, will be able to default or he will be able to make his payment on time. So with a sample data set that you have provided, as you can see, the model has exactly predicted that the customer will default. So in conclusion, I'd like to present you the numbers for the model that we have predicted and used. I think the highest observations for logistic regression and the feed-forward neural network with TensorFlow and Keras are performing well. The random forest classification, like we said, would not be an appropriate measure of the accuracy and the AUC. Thank you for staying with us. Have a great time.